Okay, here we go. 4.1, antiderivatives and indefinite integrals. So this is asking us to find the general solution of the differential equation. So let's go ahead and isolate the differential y like we've done in our, let me make this thinner. All right, so we're going to swing over the dx, and so we're isolating the differential y. And so what they're really asking us to do when we're solving a differential equation is we're really asking, hey, can you get back to the position function that had this 4x plus 1 as its derivative? That's what it's saying when it's asking us to solve a differential equation. So to solve, to get back to the position function, I know, well, wait a minute, I can't have differential y. I need regular y. I wish there was a sign that could undo differential y. And there is. And that's where our integral sign comes in. So our integral sign undoes differential y and makes it a y. But we know that we are in an equation. So whatever we do to one side, we have to do to the other side. So we've got to take the integral of the other side. So here we go. So now we're stating it a little more clearly. If we could just find what the integral of 4x plus 1 is. Now, see this dx? Anytime you write an integral sign, you better make sure you've got a dx or a dt or a d, whatever we're taking the derivative or the integral with respect to. Otherwise, we can't move forward. All right, so now it's saying, all right, at least we know that we've got our position function, y equals. Now, how do we find the integral of 4x plus 1? So remember, when we see an integral problem, it's asking us to go ahead and find the function that had this as its derivative. And so this one's pretty easy, right? Would you agree that if we had 2x squared, that would be, if we took the derivative of that, that would be 4x? And if we just had plain old x, that would be, the derivative of x would be 1. So we're just going to use a little logic here. And then we are going to add something. We're going to add a plus c. And we'll talk about why in just a second. All right? So let's go ahead. And the plus c stands for a constant because, oh, I'm getting tripped up in my microphone. All right. So let's switch over, see what's behind these things. Okay, yep, that's called the integral sign. Oh, 4x plus 1 is called the integrand. So whatever we're taking the integral of, that's the integrand. And then this is called our general solution. Real quickly, let me see if I can move forward and see. So the general solution, like if we did, let's do this one real quickly. If we went ahead and we swang our dx over, right? We undid the differential y with integration, so we did it on both sides. And we know that if I had what, x squared over 2, once again, we're going to talk about this. If we had x squared over 2, we could write that as, let's see if I have this behind here. Oh, I just have x squared over here. All right. Well, you know what? You get the point. If we had x squared over 2, it's not going to let me. Let's do this real quick. Let's see. Come back to that. Let's do this. All right. So if we had x squared over 2 plus 2, and we took the derivative of that, we'd get right back to x, wouldn't we? If we had x squared over 2 plus 3, and took the derivative of that, we'd get right back to x, wouldn't we? So once again, this is why we're doing the, besides the x squared over 2, we're doing the plus c. Plus c, that's a constant, and the constant can be anything. It can be a positive number or a negative number. We use the plus because the c can stand for anything, any real number, right? All right, so let's go back to what we were doing. This is, let's get rid of these again. Let's see. So the solution of a differential equation is the general equation that has the integrand as its derivative. That's why it's referred to as the antiderivative. All right, so there we go. For those of you already integrating with Physics C, that's the official way to build an integration problem. A lot of times when we see an integration problem, they just jump straight to this. This is all you see, right? But this is really starting with our differential equation and how you move down to find the solution to the differential equation. All right, let's see. All right, what's the rule to undo the power rule? Because so far we've just used like common sense. So we're just going to take whatever our, so we really right now are only undoing the power rule. We're going to learn other rules, other things to undo, but today it's just the power rule. So we're taking the n and we're adding 1 to it, and then whatever this number is, that goes down into our denominator, get rid of it, and then we have to remember about the plus c. So that's undoing the power rule. Feel free to pause at any time you need to. All right, find the indefinite integral, then check by differentiation. So we're going to always be able to check as we're working. All right, the first thing I'm going to do is I am going to, now note, we don't even see the dy dx. It jumps straight to the integral problem, okay? But we know what they're really up to. We're really trying to find the position function. So the first thing I'm going to do is I'm going to rewrite. I'm going to go ahead and pull that square root of x up and say it's -1/2. All right. Now, can I use that nice little rule that says add? So I'm going to go ahead and write this. I'm going to rewrite it so that you can see what I'm doing. So I'm going to add 2/2. Okay. And when I do that, I'm going to get what? Oops. Not, you know what? I'm sorry, because I don't need those integration signs. So we're just going to add the 2/2. And what are we going to get? We're going to get +1/2. So that means I have to divide by 1/2. So let's see what we've got. We've got -1/2 plus 2/2. That's x to the 1/2. And then we're going to have 2 divided by 1/2. Whenever we're dividing by a fraction, right, it's really multiplied by the reciprocal. Anyways, but 2 divided by 1/2, that's pretty easy. That's going to be 4. And we're going to rewrite it in a nice way. And then if we were asked if we wanted to double check, we would just simply rewrite. Well, we already know the square root of, the derivative of square root of x is what? 1/2 square root of x. And so 4/2, that's right. We're right back to where we started from. So we can be like, yay, we did it. All right, now, what did I forget? So easy to forget. I forgot my plus c. Let's say on a test you do all this hard work and you forget your plus c when doing an indefinite integral. That is okay. I will not take off for that because you know what? We all forget our plus c's. In the homework, though, just really try to remember plus c, plus c, plus c. I don't think the AP exam is going to take off for that, but you know. So once again, indefinite, let's go back to why we're calling this an indefinite integral. It's just, there are no bounds. We're going to do integration problems where we've got bounds, we've got upper and lower bounds, and we're actually going to get an answer, not just a solution, a general solution. All right. Go ahead and write this down, and let's just talk. So obviously pause when you're writing it down. Let's talk about, right now, if we didn't rewrite it, we don't have the ability to integrate this. And honestly, when we learn more advanced ways to integrate, we are still going to do it exactly the same way we're going to do it today. So what's that going to be? It's going to be expanding it. So go ahead and expand the binomial and come back. Let's make sure you expand it correctly. And then bam, we just have a polynomial. And polynomials are the easiest thing to take the integral of, right? We're just going to do step by step. So feel free to pause before I reveal. And there we go. There's the big reveal. Okay. So remember, when you are integrating, before you start actually integrating, rewrite. We had to rewrite for the first two problems that we've done. All right, go ahead and pause and write this one down. Obviously, we are going to rewrite this. So we are going to split it up into two fractions. And then we're going to continue. After we split up into two fractions, we're going to continue to rewrite. And then once we're done rewriting, we're going to take the integral of each piece. Note that when you have terms, different terms split up, terms are the things that are split up between pluses and minus signs. You take the integration of each term, just like we took the derivative of each term, same thing here. And then finally, let's rewrite, when we get to the position function, let's rewrite it so it looks nice. So hopefully I'm giving you enough time to pause before I just go right through. I am trying to save time. I am filming this during my lunch half hour, and I want to eat. All right. Okay. All right, go ahead and pause this and write it down. We want to absolutely rewrite it. We want to go ahead and distribute. Oh, before we distribute, we want to rewrite the cube root as a 1/3, then we'll distribute. Okay, now we're just dealing with two separate terms. We're going to integrate using our little rule where we add 1 to the exponent and divide. And it looks like I didn't really care about rewriting it, or I guess I did rewrite it down here. I'm fine with either way on the test. It's really just about looking when you're taking the AP exam multiple choice, just recognizing that these two forms are the same thing. And if you have one form and they have the other, you can still recognize it, right? And pick the right answer. Okay, pause and write it down. I was really surprised, and I'm talking to the 2025-26 group, that you all did not ask me before the chapter 3 test, is there trig on it? Because the answer will always be yes. Every single test has trig on it. It never goes away. So here it is. I don't recognize, I know my trig derivatives like you do, and I don't recognize any yet. So I'm like, you know what? Let's go ahead and distribute and see if that helps us out. So when we distribute, we're like, yes, we've got secant tan, that is a derivative, because if you're seeking, what are you seeking? You're seeking a tan. And then we see here secant squared, that's the answer to a derivative, because if you're tan, that means you seeked it twice. And there we go. We've got the secant, we've got the tan, we brought down our minus sign, right? And we've got the plus c. So if you do not have those trig derivatives memorized, you got it. You can do it, right? If you're tan, it means you seeked it twice. If you're co-seeking, what are you co-seeking? You're co-seeking a cot. If you're seeking, what are you seeking? You're seeking a tan. If you're already in the cot, you probably co-seeked it twice. Now, the ones that have sign in it, whether it's sign, oh gosh, it's not going to let me write on it, is it? Let's see. Whether it's sign or sign in disguise, right? Negative cosecant is cosecant is 1 over sign. Same thing here. So if a sign or cosecant in it, it's also going to have a negative. So if you don't have those memorized, memorize them. All right, pause and write it down. All right, remember how we broke this one up into two fractions? We could do that because the bottom was solid, all right? Over here, this is different. And you're like, of course we know that, Miss Overby. No, there's so many people that would split this up into cosine of x over 1 minus cosine of x over cosine squared x. Hopefully that wasn't you that would think about that, but somebody always thinks about that. So no, we're not going to do it. We also recognize we can't do anything right now. I mean, obviously we could take the integral of the top, but we can't take the integral of the bottom. And guess what? That's not the way it works. We're not allowed to take the integral of the top and the integral of the bottom. We can take integrals separately of terms, but this is one term here. This whole thing is one term. So what's 1 minus cosine squared? Let's remember our identities, right? That's going to be our sine squared. Now we're cooking. We can do something now. Because if I see that sine squared x, that's sine x times sine x. And I know something's going to happen. Let's go ahead and pause. You write it down. So there we go. We've got cosine over sine. We've got 1 over sine. Use your identities. Cosec a cot, right? That is our cosecant. If you're coseking something, you're coseking a cot. The only thing this is missing is the negative. If the negative were there, we wouldn't need the negative in our answer, all right? But this is the derivative of negative cosecant, and plus c. All right, now we're going to get to particular solutions These are still indefinite integrals we're going to be working with, but they are particular solutions that are particular to what the initial position. They're going to give us an initial position, which just means they're going to give us a point from the position function. All right, so we're going to do the same thing. Go ahead and pause, and why don't you go ahead and integrate this and come back. All right, so we've got the 3x squared plus c. Now, we can get rid of this c by using our initial condition. This says x is 1, so we're going to take that 1 and plug it in for x. This says y is 7. We're going to plug that in for y, and we're going to solve for c. Oh. Okay, that is not helpful. Let's see if I can undo that. Okay. Down. So we plugged in, we get c is 4. Okay. Now I want you to know this is still different than a definite integral. A definite integral will have bounds. It'll have a number here, it'll have a number here, and when all said and done, the answer will be a number. But this is nice when we have particular solutions to a differential equation, because at least we don't have a plus c anymore. We know the exact position function that we're looking for. All right, let's see what else I have behind these boxes. Find a function whose derivative is 6x and where f of 1 equals 7. Right, that was just a little translation there. What do I have here? Oh, that was the box I was pulling down. All right, let's do another one. All right, you know what? Let's pause. You know how to do this. It's the same exact one as we just did, so pause the video. All right, here we go. Hopefully that's what you got. Pause it, because I'm moving on. I got to eat. All right, this one is the same thing. We're finding, and I noticed that example 2 and 3 did not have any instructions. So particular solutions to differential equations, that's kind of like, that's not even a direction. Find particular solutions to the differential equations, probably given initial conditions. That would be a much better, but I just don't even have the words. All right, so here we go. Note that they're giving us the second derivative. So what do you think we're going to have to do? If they're giving us a second derivative, well, we're going to have to integrate to get back to the first derivative. And we'd have to stop there because it'd be a plus c. We can't move backwards from the first derivative to the position function if we have a c, right? You can't integrate an integrand that has a c in it. So we're going to use this to find, so when we integrate the second derivative, we're going to get back to the first derivative. We'll have a plus c. We're going to use this, plug it in to solve for our c. Then we have the first derivative we can take the integral of, and when we're done with it integrating, we can use this to solve for our c. So ready, set, go, pause it, and come on back. And what's behind here? Okay. Did we get everything? I guess in the end, I plugged in a 1 and I got a 2. I don't even have that. Doesn't look like I have that work done. But all right, hopefully in the end, we all got the same thing. And I think that's it. All right. This lesson is important because when we get to our upper level integration, we still have to remember this, because sometimes that will be snuck in and we'll be trying, like busting our brains, trying to figure things out. And it's like, just rewrite it and undo the power rule, or just rewrite it and use the trig derivatives, right? All right, thanks for joining me.